So we did Ampere's application of Ampere's law. In the last class. Okay. If you have any current, any number of currents, let's say some I1, I2, I3, some going in the opposite direction, I4, anything in an area, and you take a loop around it of any shape, okay? An imaginary loop around it, an infinitesimal element, let's say dl, then the line integral of the magnetic field around this loop is equal to mu naught times the total current, okay, total current inside and closed. So in this case it will be the sum of these current, as many currents as you have, okay? So that's the thing. If it is a volume current going, let's say it's a continuous current, so you have some sort of wire or something with some volume current going on inside, and the volume current density is let's say J, then of course the current enclosed will be J dot dA, where dA is this area element of this thing, okay? So this will be your total current enclosed. So we did application of this, and it's useful only when there is a symmetry. For example, Gauss law is any for example, that last class of the you have one charge Q, then you can take a sphere around it, okay, at a distance, the radius is r, let's say, and then the magnitude of electric field is the same here, same everywhere on the surface of this sphere, right? Because it depends on 1 over r, because the r is same, so the magnitude is same everywhere. And that's why actually when you have E dot dA, because this magnitude is constant on this surface, you can take it outside. And that's equal to what? Q, total Q by epsilon naught, right? Total Q inside. So one charge and epsilon naught, and it's just the area, so 4 pi r square, and you get the E. But suppose you have another charge with a slight separation, then this method is not anymore applicable, because drawing a sphere, you can draw a sphere and you can still write E dot dA equal to your Q1 and Q2, let's say Q1 plus Q2 by epsilon. That's true, you can still write this and this is valid, but you cannot pull E outside now, because the value of E is not same everywhere on the surface, because the distance is different at different point from the two charges, and therefore E is not constant and you cannot pull it outside the integral, so it's not useful anymore. Only in very symmetric situation you can pull this out. Like if you have a infinite line charge in an infinite line, then you can take a cylinder, and everywhere on this cylinder, even here, everywhere on the surface of the cylinder, again the magnitude of the electric field will be constant, because at the same distance, and you can pull it outside an area of the cylinder and you can get again. But you have two line charges, or the charge is slightly like this, and it's not applicable anymore. But the integral form is valid. it will be just different at different point, and so the integration will still turn out to be total charge divided by epsilon naught. So Ampere's law is like Gauss law in magnetostatics. It is equivalent, analogous of Gauss law. Okay. It is like the E dot dA, and that will be your surface integral. This is the loop integral, equal to total charge for Q enclosed by epsilon naught. Okay. So once again, you need a symmetric situation. So infinite charge current, yes. You can take a loop. A loop could be like this around it, and then magnetic field will be same everywhere. So you apply this for a line charge, for a solenoid, for an infinite sheet of actually charge, and we found magnetic field. I gave you a problem of finding the magnetic field of a torus. Torus is like this. A donut, you know. This thing. You can take a long solenoid and bend it to form a torus. Let's say there are n number of total turns. So if current I is flowing, then it's I, right? Everywhere. Okay. What loop can we take here? There are two situations. What is inside the the torus, and what is outside? So for outside, we have to take an outside loop. We can take a loop like this, a concentric circle, okay, with a radius, let's say S. Now, B dot dl, okay, over this loop. So to mu naught, what is current enclosed? What is the total current passing through this loop? Kiman hobo? 0. It's like going in a loop, right? So whatever is coming out, it's going inside. So basically 0. So this side is 0. And this is nothing but constant on every point. So B comes out. And what is the total of dl? Is 2 pi s perimeter equal to 0. And that gives us the magnetic field strength is 0. Everywhere outside. Just like the solenoid. Now for the inside, we can take another loop that passes through inside. Okay, once again the same. B dot dl equal to mu naught. Now how much current? I going inside. How many times? So you have just, going inside. N number of them. N number of times. So N number of times. That's your total current. Therefore, 2 pi s equal to mu naught Ni, and that's it. That is the magnitude of magnetic field. Now for the direction, it depends. If we take current like this, then you can figure out. So if I take current like this, so it will be in this direction. In this case, it will be minus phi direction. If we take the current in the opposite direction, that will be plus phi. So it's up to you. Here we took this direction, so it turned out to be minus phi, clockwise. Okay. for the opposite, take it opposite, then it will be nicer, positive. So that is it. Okay. Inside, outside. Okay. Oh, actually, I wrote a point as well. Yat lole ki hobo loop. It's still outside, right? No currents passing through it. So again, it will be 0. Magnetic vector potential. Have you proved that del cross E equal to 0? Right? Curl of electric field is 0. It means electric field is not rotational. I mean, curl of a gradient is 0. Gradient of something is always 0. Eto mathematics of definitely asil. Mathematical physics of last semester. Mane gradient mane ki? The highest gradient is change, three-dimensional partial derivative, directional derivative, right? Del x of phi, I cap and this. And the direction is the direction of highest change, okay? Increase or decrease. And it is irrotational. So curl of a gradient is always 0. So tar mane, when we see that curl of electric field is 0, if curl of electric field is 0, and we know that curl of a gradient of something is always 0, so it tempts us to write that E must be some scalar. If we do that, then obviously curl of E will be identically 0, right? Now if you take curl of E, it will be just curl of this, and this will be 0. So that is a scalar. Gradient is on x on a scalar, right? Gradient of a scalar. We have a similar situation here, but I mean, unfortunately, curl of B is not 0. It is, you know, mu naught J. I mean, exactly integrating this, you get the integral form of Ampere's law, right? How do you do it? This dot dA, and you do a surface integral, right? So then J dot dA surface integral becomes just current inside, and this dot dA, then you apply the Stokes law and you get the line integral. And so you have the integral form of Ampere's law. This is the differential form of Ampere's law. We did that. We proved that in a whole class. Anyway, so we see that curl of magnetic field is not 0. Right? Curl of magnetic field is not 0. And therefore, we cannot apply the same technique like when we saw curl of E equal to 0, we wrote E equal to some gradient of some scalar. Unfortunately, we cannot do this here. We have something sitting here. I mean, unless you had space where there is no current. Okay? If there is no current, then J becomes 0. And in that special condition, yes, del cross B equal to 0, and you could write B equal to gradient of some scalar, but that's not always true. Like in general, it's not true, like electric field. So it's not very useful. Instead, we have something else. We have del dot B equal to 0. This is always true in magnetic field. So divergence of magnetic field is 0. So magnetic field, that I discussed, that this means magnetic is very important, remember. Monopoles don't exist. Divergence of electric field is not 0, because if you have a single charge, field can diverge from it in all direction, you know. Actually, a better way of drawing it is you have higher strength near. I mean, there is lines everywhere actually in space. So we cannot draw infinite number. So we draw some representative. And then magnitude rate. And then even smaller. Because it's dropping as 1 over r squared. Right? Because the sphere is increasing as the surface of the sphere is increasing as 4 pi r squared. So this is dropping as 1 over r squared. And this clearly has a divergence. So if you take an area, surface area, electric fields are diverging from a point. But this sort of situation, so that's why del dot E is not 0. But this sort of situation does not exist in magnetic field. You do not have an isolated north pole, just north pole. No. It's not possible that you have just north pole from which magnetic field is coming out of in all direction, right? It's not possible. There is always a south pole. So it forms, so magnetic field lines always are closed. So they go outside and then come back, and inside the magnet they form the loop. So they are always in a loop, magnetic fields. They are not open. Okay? And because of that, it doesn't matter where you take your surface. You take it here, then yeah, equal amount is entering, the equal coming out. You take it in a bigger one, then of course. So that's why the del dot B is 0. The divergence of magnetic field is 0. And this tells us that there is no monopole. There is no single pole. Okay? This is important. Okay. Because B is rotational. All right. Now that del dot B is 0, if you did your mathematical physics seriously, then you know that divergence of what quantity is 0. Electric field on AC. For example, curl of a gradient was 0. Divergence of what is 0? Divergence of a curl is 0. So if you had any curl of some other quantity, delta say, so it's rotational. So this is curl of, let's say, some quantity A. If you take a divergence, this will be identically 0. Okay? So when we see that divergence of magnetic field is always 0, it comes to our mind, maybe B we can write as curl of something, right? We can write B as curl of something. Let's do that. And we name it again potential, but this is not a scalar, so this is a vector potential. I mean, it's not going to be as useful, at least now, as the scalar potential. Scalar potential had the benefit that it's a scalar. So instead of, calculating electric field, which is a vector, and we need to take care of the magnitude as well as direction, while, for example, you have a a charge loop like this, line charge, and then you need to calculate electric field here. Then you had to like calculate at each point electric field due to this small element dE and its direction, and due to another piece and its direction, and then do the vector sum, which is difficult, right? Which is difficult because you have to do a vector sum. You have to take care of angles and everything because of direction. Instead, we could just calculate a scalar quantity phi that has no direction. So we don't care about the direction. We calculate the scalar potential due to all these charges, and then just do a normal sum because it's a scalar. And in the end, just apply a gradient of this, and that's electric field, right? So it was useful. We can get electric field out of a scalar, a vector thing out of a scalar. Here it's not that useful because A is again another vector. So I mean, again vector sum and all these things will be involved. But this will come much later, that why a vector potential is so important. I mean, vector potential is at the base of theoretical development. I mean, all theoretical physics development, all the particle physics, quantum chromodynamics, if you have heard about, the theory of quarks and gluons, all the nuclear forces, weak and strong, all the theory of these things and standard model of physics, everything is inspired by this vector potential. Okay. Much later we will come to the why this is so important. But for now it seems like unnecessary. Just why? I mean, we could just calculate magnetic field. Why introduce another vector like this? But anyway, so how do we calculate magnetic field? Of course, using the key quantum chromodynamics. Chrome means color. So color charge. Quarks, the forces between quarks are exchanged by particles called gluons, and they come in 8 types. Fundamentally there are 3 colors, red, green and blue, not our physical red, green, blue, just names, just tags we used as RGB because there happens to be 3 fundamental, but that's why it deals with color charges, and that's why chromodynamics. Okay, so how do we calculate magnetic field? Once again we use Ampere's law. Ampere's law in differential form was just this, remember, right? And if we put now this expression in place of B, then we have del cross A, and that is gradient of, you should remember these, you might have forgotten, del cross A is del, gradient of del dot A minus Laplacian del square of A equal to mu naught J. Now this is a long and complicated, slightly complicated equation rather than this. This was just del cross B equal to mu naught J. Now in terms of A, it has become slightly longer. Okay? But why are we doing this? I'll come to that soon. Let me write it here. I'm saying that we can always put del dot A equal to 0. Now why? Why we can do that? So look at this. Okay, if we did that, if del dot A was really 0, then this part is gone. So we will just have our Ampere's law would have just become del square of A equal to minus mu naught J, right? This is called a Poisson equation. Poisson's equation, okay? And I don't know if you got this in electrostatics or not. In electrostatics, it will be in this form, del square of phi equal to minus rho over epsilon naught. Okay? Exactly, this comes again from your Gauss law. So there you put this E equal to minus del phi in your Gauss law and you get this. Here we put the B equal to del cross A in our Ampere's law and we get a Poisson's equation, similar, okay? And if, I mean, just for now, assume that yes, we can put del dot A equal to 0. I'll come to that why. And but if we did that, this will be the equation. And this is basically what? Collection of 3 equations. Because these are vectors. Not like scalar, okay, del square phi equal. These are vectors. So one will be for AX, JX, AY, JY, AZ, JZ. So it will be like del square A I, let's say, equal to mu naught JI for I equal to X comma Y comma. So there are basically 3 equations, 3 Poisson's equation. And just like electrostatics, if the condition, so in electrostatic, one condition is that charge density must go to 0 at infinity. Whatever charge you have must be confined in a finite space, right? It cannot go on forever. So if that was the case, the solution was like this: phi equal to 1 over 4 pi epsilon naught d tau prime rho of r prime by r. This was actually the solution. And you should kind of remember this from your even higher secondary. For example, if it was a single charge, then rho d tau is just charge. So potential is just 1 over 4 pi epsilon naught q over r. Right? For a single charge, it will be like this. In case of a charge density, then this is basically your charge. Right? A charge element here, 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 here. So this is sum over all these charges divided by this. So this is potential. And this comes from an equation like this, concerning del square phi equal to minus 1 over epsilon naught rho. Okay? And that's the solution. So it's the solution of del square phi equal to minus rho over epsilon naught. Now minus 1 over epsilon naught here is similar to minus mu naught. So therefore 1 pi 4 pi epsilon naught, we can replace it by mu naught by 4 pi, because mu naught is here, and there it was 1 over epsilon naught. And the phi we can replace by ai, and the rho we can replace with ji. Right? Because it's the same equation. But the condition again applies that the current must go to 0 at infinity. And then we know the solution already from our electrostatics. We can just, because the mathematics is already done there and the solution is known. Because the equation is same, we can write down the solution. Okay? So we have a nice solution, I mean, what is A? So if we can calculate the A in a straightforward way. I gave you a current density. I give you whatever current density is, some function, okay, some complicated function or whatever. I give you a J and I ask you, calculate the magnetic field. It's very difficult, complicated J, okay. You can put that complicated J here and just integrate it. Maybe you cannot do the integration. You can use computer. But you can calculate this integration using a computer, right? In the end, you will have an AI, meaning AX, AY, AZ for JX, JY, JZ, 3 of them. Then you have A, then you put your A here, do a curl, and in the end you have magnetic field. It's a straightforward algorithm, right? Straightforward algorithm. You have this formula and you can calculate B. Earlier it wasn't easier. Okay? So yeah, that's it. Now coming to the point, we put del dot A equal to 0 by force here. And that's why I got this nice equation like electrostatics, and we could write a solution like this. But in actually it was not so, right? There was this term. How can we set this equal to 0? So I'm coming to that now. So del dot A equal to 0. Before that, this is I enforced, okay? I chose actually. It's not always true. It can be anything. I chose that I will take those A that has del dot A equal to 0. Now this freedom actually we have. If you look at this equation, A comes from this equation. B must be curl of A. Now B is curl of A. That means you can add anything with A which is constant. It is imagine in case of scalars. Let's say you have a function f of x, okay, which is equal to, let's say, del x of some other function gx. What does that tell you about gx is that you can take gx equal to some gx and you can change this by adding a constant term. Okay, that does not depend on x. And now if you take del x of gx, it will be again del b by del x plus del x of c, which is 0. Again the same effects you will get, right? Any constant you add or any function of y, and it still will be the same effects. Now what is physical? Magnetic field is physical. Okay, magnetic field is something that we measure. That's something we feel. A is not physical. It's a mathematical artifact. We can write magnetic field in terms of some mathematical function A, but B is what we really measure. Magnetic field, electric field, that's what we can feel. Magnetic field, if you put a compass, it will be pointing towards its direction of the lines of force of magnetic field, right? Towards the north. That's your real physical quantity. A is not. So I can change A in whatever way I want, and in the end, if I get the same magnetic field, then it's okay, right? Life is cool, because I mean, in the end, B is the real thing, A is not. So here, imagine like F is your real thing. It's some field, let's say. G is not. I can write F in terms of some G. Okay? And then with G, you have the freedom to add anything. Anything that when you take del x, that part goes to 0. So G is as good as Gx plus C. Right? The same thing. Okay? Why this is useful here? So, in similar situation, now really focus on this. B is del cross A. What can we add with A that will not affect B? We can add something with A, the curl of which is 0. So I can take like A going to some A plus what has curl 0? Gradient of something. I can put gradient of some whatever, lambda, another scalar. If I do that, now take curl. Curl on this A. What will happen to this? It will be curl of A plus curl of this del lambda, right? But this is 0. Because curl of a gradient is always 0. So once again, your curl does not change if you add a gradient with it. So if you replace A by A plus gradient of some lambda 1, gradient of lambda 2, whatever, those are going to be 0 when it comes. So physics remains the same. This change does not change the physics, and so we are allowed to do this. And because of that, now look at this. This is allowed, right? This will not, this transformation, let's say, will not impact the physics. This transformation has a name. Just, you don't have to remember this. Just in your future, it might click. It's called a gauge freedom, that you can do this. It's a gauge transformation. It's a fancy name that you don't need to remember. Just I give you this information. Anyway, so you have this. Now let's apply del dot A on this. Apply divergence on this. So divergence, if you do this change, how will the divergence change? It will be del dot A plus this del square of lambda. Now I can choose my lambda in any way possible because it's just a gradient of lambda. I can choose lambda in any way possible such that this thing cancel this thing. This is complete freedom, right? Lambda. I can always choose some lambda that in the end this term becomes exactly opposite negative of this term and it cancels. So that's why I have the freedom to choose del dot. And let's say we did all this in our mind and we found a lambda for which our del dot A is 0. And we are doing this for that A. So I'm saying we can always set del dot A equal to 0. If it's not A equal to 0, we can do some fancy things like introduce some lambda that does that. And in the end we can set del dot A equal to 0. And this is the solution. I mean, if you don't do this, and if your del dot A is not 0, then still there will be some solution. But it's not simple like this. Okay? The fact that we can apply, so we know the solution of this kind of equation from electrostatics and from mathematics. And that's why I wanted to use this, ready-made, okay? And that's why I use this technique condition so that del dot A is 0. You can keep a condition like del dot A is not equal to 0. Del dot A equal to anything actually, in fact you can choose anything. You have to cleverly choose your lambda and you get anything. And then your solutions will have some other stuff, not so nice. Okay. In future electromagnetic theory you will see that there are other choices. People don't just take del dot A equal to 0. Some people take some other combinations, okay, as it suits them in situations. You have the freedom. This is called the gauge fixing. So this is what we fixed as a choice. It's called a gauge fixing. Once you do this, then you have already done with your freedom. But before doing that, you have the freedom. This is called a gauge transformation or a gauge freedom, where you can choose various lambdas and all these things. Okay. Okay, this is the end of this unit, and so anyway, last thing at a diagram we did is at a triangle, useful actually. এইটো এনেকুৱা আঁকি তোমাৰ টেবিলত লগাই দিলেও হ'ব. It's very useful. A, J আৰু B ৰ মাজত এটা ৰিলেশ্যন. Okay. So A আৰু B ৰ মাজত ৰিলেশ্যন কি আছে? B equal to del cross A. Right? B আৰু J ৰ মাজত কি ৰিলেশ্যন আছে? বিয়ত চাবাছ ল. B equal to mu naught by 4 pi d tau prime J, let's d tau, J over J cross this R by R square, right? J আৰু A ৰ মাজত just পাইছো আমি del dot এইটো আহিব only when you say del dot a equal to 0. Remember, del dot a equal to 0 choose করিলে এই সলিউশনটো পাম আমি del cross b equal to mu naught j আৰু এটা ৰিলেশন আছে j আৰু b ৰ মাজত del cross b equal to mu naught j এইটো হল তোমার ডিফারেন্সিয়াল ফর্ম অফ এম্পিয়ারস ল এইটো এই সলিউশনটো আহে del square a equal to minus mu naught j ইকুয়েশন সলভ করি সো এনেকুৱা এটা ট্রায়াঙ্গল তোমার ইলেক্ট্রোস্ট্যাটিক্সতো আছে that will be কোৱাচোন কি হ'ব তিনটা ভেৰিয়েবল ইলেক্ট্রোস্ট্যাটিক্সৰ কাৰণে ইলেক্ট্রোস্ট্যাটিক্সত ইকুইভ্যালেন্ট কি হ'ব ইয়াত ইলেক্ট্রিক ফিল্ড হ'ব a কি হ'ব a ভেক্টর পটেনশিয়াল স্কেলার পটেনশিয়াল হ'ব j আছে তা চার্জ হ'ব চার্জ ডেনসিটি ρ হ'ব ইয়াত থাকিব তোমাৰ Poinson's equation electrostaticsৰ কাৰণে ইয়াত স্কেলার পটেনশিয়াল ρ থাকিব ইয়াত ইলেক্ট্রিক পটেনশিয়ালৰ ফৰ্মুলা থাকিব ইন টার্মস অফ ρ সেম সো এটা মনত ৰাখিলে এটো হৈ যায় mu naught to 1 over epsilon naught হৈ যাব ওকে সো তোমার ইয়াত 1 over 4 pi epsilon naught তেতিয়া হ'ব ইলেক্ট্রিক ফিল্ডৰ ইয়াত বিয়টছাভাস ল আছে তাত হ'ব কুলম্বস ল ওকে ইয়াত del dot del b equal to del cross a আছে তাত e equal to minus del phi হ'ব ওকে আৰু তোমাৰ আৰু কি আছে del dot b equal to 0 আছে তাত del cross e equal to তোমার হ'ব 0 so just write it down draw it somewhere on your session or question কিন্তু এনেকা conceptual numerical problems বেছি থাকিব so assignment যিবিলাক মই দি থাকো এইবিলাক কৰিলে sessional easy হ'ব